So welcome everyone to this 14th session of Statistical Learning in Practice. As I just said, we'll begin with, we'll finish introducing linear classifiers, and then we'll begin with nonlinear classifiers. So what's the next? So remember we spoke about linear discriminant analysis, in which the assumptions that we were making is that the distribution of the covariates given the label was a Gaussian distribution, and then from that we also assumed that the proportion of classes was proportional to the observed data points, and from that we had basically all of the data generating mechanism, and we could therefore try to fit the model and see what happens, and then we did that in practical. So today we're going to talk about logistic regression classification, which is, as you can expect, quite related to logistic regression that we did, and we've briefly seen this in the practical. So hopefully what we see today will end clarifying the few things that may not have been too clear because they hadn't been covered in the theory. Okay, so let's start by making an analogy with logistic regression. Okay, so this is 2, 1, 2. Okay, so 2, 1, 2. Logistic regression classification. You could omit a regression. LRC. Okay, so let's recall that in logistic regression model, what we were modeling was yi given xi, independent according to a binomial distribution with parameters mi, p, xi, right? And then the model for the probability was the following. So we assumed the logit function of the p, which is to say this quantity, was basically the linear predictor. Yeah. So the linear predictor being in this case written. So in this section we're going to write the intercept term explicitly. Okay, so unlike in regression where we were always hiding it in beta. Okay, so we write this, and then given this setting, there we were only allowing for two class, because the binomial model essentially allows you to take ones of zeros, maybe to aggregate some of those to get the MI. But essentially, if you were thinking of deaggregating them and just having individual 0, 1s, then of course this could only work for two class classification, right? So then let's think about when that is classifying into one or the other class. So let's first fit the parameters and then see what happens. So if this is the MLE, then two class classification let's see, occurs two class classification via logistic regression model, I guess, or in this case we could also say LRC, because right now they are the same thing, occurs depending on the value of our estimated P, right? And what is this? Well, this is the exponential, this beta naught plus X transpose beta hat divided by 1 plus the same quantity, okay? And what matters is whether this quantity is greater than 1/2 or not, right? Because if it is greater than 1/2, then we say, well, I clearly want to accept the class, the class with label 1 as the one, as X, excuse me. So if you're given an X, then we will classify it as the class with label 1. And if it were less than or equal to 1/2, then we could say that we accept class 0 for the observation X, right? Okay, and this equal, is arbitrary where we put it, so we just put it for the less than, okay? Okay, so fine, but there is yet another way in which we can do this, which is, or equivalently, it can depend on, okay, so let's read the phrase. So the MLE, so if this is the MLE, the two-class classification via LRC occurs depending on this, or equivalently, depending on the sign of the guy in the function, right? So depending on whether this is greater than 0 or less than or equal to 0, right? Why am I writing this? Well, because really, this is really the quantities that we're going to be looking at. Yeah. Okay, so for L classes, let's generalize this. So for L classes rather than 2, and note that I was implicitly talking about 2 classes with the labels being 0 and 1 in the binomial experiment. So we may be changing the labels often. But so in this case, we're going to be, assuming that we have 1 to capital L as the labels. So let's assume the second way of viewing the random variables or the response random variables. So let's assume that these guys, given these, are independent as usual, but come from a multinomial distribution with parameters 1, P1, xi, up to PL, xi, okay? And now let's model each of these P's. So where PL of X, and because we're going to have a model similar to the above, we're going to have also some parameters which are going to be vectors. And so we can write here just the regressor. And then okay, so this is for X, yeah, okay. And then XL. What we assume is something very similar to the above, yeah? So it satisfies that the log of the ratio, these guys, this is the first element, is going to be equal to this here. So this beta L is beta 0 or beta, let's see. Yeah, okay, so let's say beta 0L and beta L transpose and transpose. So the only difference between the whole vector, and the second part of a vector is the underline. Yeah? And these guys are going to belong to 1 plus p. Okay, so again, we're going to be separating this intercept type of parameter. And of course, this is for L in our usual labeled space. And we're going to take as, by convention, and this would be the whole thing. So the whole thing of the whole parameter of the first class to be exactly 0. Okay, and if we do that, we have, we recover the above. Okay, for the two class classification. Okay, but we can also equivalently write, so, or again equivalently, we can write directly the model onto this conditional distribution, which is then given by, so remember that we're keeping in mind this decision theory and what we model in it. And so we're going to model these things directly, written as this, yeah, which is to say that it's prime, which is to say that the probabilities are going to be proportional to these numerators. Yeah? So pretty intuitive quantities to be looking at. Okay. Okay. So let me yet give you. So I mean, we've written this using the multinomial form. We could have, exactly in the equivalent way, written it with the categorical way of writing the labels. And let us now take that view of the categorical, but simply because it's just slightly simpler notationally to write the log likelihood. But these things are completely interchangeable. So let's assume yi xi independent categorical, just so that you have this clarified. And then we have the P1, maybe actually, given that we're doing the modeling already, let us write 1 to capital L. Okay, so if we have this, then the log likelihood is given by L beta 1 to beta L. Let's have all the underlines. There's going to be the sum over all the data points that, of course, comes from independence, and then this. So you see, this is a bit easier to write with this categorical form. Excuse me, if I write it correctly. Okay, and then here we have the log of our etas. Okay, so we've now sort of set up the problem. So we now have a model. We now have a log likelihood, so we can fit it, and we can find MLEs, and then we can say something about the estimator. So let's assume then, or let's call then beta 1 hat to the 0 vector, because that's the convention. We could have taken any other. Yeah, we could have taken the beta 2, or we could have taken the beta capital L. And you can, if the problem somehow naturally gives rise to to any of those choices, then you're absolutely free to do that. But it's just to keep the convention going, because this agrees with the logistic regression problem. Okay, so then we have this, and the other thing we have is the beta 2 up to the beta capital L. These are going to be the MLEs for beta 2 up to beta capital L, right? Okay, so now we're ready for the definition of the classifier, which is that the logistic regression classifier is given by this guy, that we classify a given X in R P, in this case, according to the argmin. This is now over all of the possible labels of this discriminant function, which is in itself given very simply by this product here. Okay. So you understand now why I sort of started, or why I emphasized this form, this actually this linear form of the classifier at first, of the two-class classifier. Okay, so indeed this is a classifier. This is a linear classifier. Yeah. So if you compute the classification boundaries, then of course they're going to be depending only on the discriminant function, which is linear, and so on. Yeah. Okay, so let's make a couple of remarks. First, the good news is that logistic regression classification provides more than a classifier. Right? What we have is that these quantities here, let's see, so exponential of 1x beta L, this to the -1. If we multiply this by each of the numerators, then these guys is the vector of estimated probabilities of X being in each class. Okay, so it's more than just classification. And then, of course, what we're doing when we try to classify is to look at this. What we're implicitly doing, at least through the definition that I've given, is to be looking at all of these probabilities, estimated probabilities, and taking the one with the largest value. Okay. Okay, and then second, so now remember that we're trying to optimize the log likelihood, right? So this guy here, guy at the top. So this log likelihood, this eta, or these etas, which, yeah, so far, I mean, each of them depends on betas, different betas, right? Because they are given here. So of course, the length of the beta is going to be given by p, or maybe p plus 1, and then we're going to have capital L of them, or maybe capital L minus 1 of them, but anyway, that doesn't matter. So we're going to have really of the order of capital L times p parameters. Okay, so if we have that and we wish to estimate the values, and we do so through Newton-Raphson, in which we need to compute the Hessian, then the Hessians are going to depend on this. So the dimension is going to be the product of these quantities, so P and L, and it's going to be very costly when any of those two parameters are large. Yeah. So So let's write that. So when P or L are large, computing Hessian of star, where star is going to be this. Okay. So computing the Hessian of star, i.e. the log likelihood, is expensive. Yeah. Okay, so we introduce an alternative. And this is an alternative, of course, to Newton raphson. Yeah? Because I'm implicitly saying that we were going to find the zeros with the zeros of the gradient with Newton raphson. Yeah? Which is what we've done, basically, traditionally. And so this is gradient descent, which should be familiar to most of you. And it only requires first derivatives. So we can avoid the use of the Hessian. Okay, and I will shorten gradient descent as GD, whatever is needed, like now. So GD, what it does is to minimize. Of course, minimizing is the same as maximizing the negative of whatever function you're looking at. So it doesn't matter whether we write minimize or maximize. So minimizes a differentiable function f going from Rd to R over Rd. So we don't have any restrictions as follows. So first, choose an initial point. So choose theta 0. This, of course, belongs to Rd. And then second, we choose, or we set theta t to be the previous value minus, and this is because we are minimizing. So if we were maximizing, you can just add a write plus. So this times the f at the previous one. Yeah? Sorry, with a gradient, of course. So let me maybe just leave a bit more space. The gradient with respect to theta. Yeah, which is so d here would be something of the order of capital L times p. Yeah, so that's the order of theta. And this is the gradient of f evaluated at the t minus 1. Okay, and so for how long do we do this? Well, we do this for 1, 2, etc. until numerical convergence. Okay. So just a final remark about this is that, and this is about gradient descent, so what really matters here is choosing this step size. Yeah? So that's actually critical. Okay, so the step size, because I mean, remember, the gradient is the direction of maximum increase. So of course we're taking the negative gradient so that we decrease, but this is true, the direction, that direction of maximum change is true, for a neighborhood of the point that you're looking at. So by taking this alpha t greater than 0, then we are giving a step that may be a bit too large, and so that's why it's critical. So the step size, or in machine learning, is also called the learning rate. Alpha t should be or must be carefully chosen? And if so, if so, there is convergence to local maximum, or in this case minimum. It's to local minimum. Okay, so under sufficient assumptions on the learning rate and the function, then you get this convergence. Okay, so I will give a reference in the notes. Okay, so next topic, which is optimal separating hyperplane and support vector machines. Which I shorten as SVMs. Okay, so let me see if I can speed up a bit. Okay, so far we've been in LDA and LRC. We've been looking at a multi-class classification. So here, instead, we're going to focus on let's see if I can fit this. Okay, so here we're going to take two-class classification here. Which means that we can take this L to be -1, 1 without loss of generality. Okay, so we're changing the labels to, from 1 and 2 to -1 and 1. Yep. And this will be just basically for mathematical convenience. And you'll be wondering, okay, so what if we have more than two classes? So if you have more than two classes, then there are a couple of options. So you could just be looking at all of the possible pairs, right? Comparing them, comparing classes one by one, and then having some sort of majority voting, for instance. Or you could also just simply take a class and then compare it to another class, and then as soon as that class is chosen, then you change and compare to other classes, and then you try to therefore decrease the number of comparisons that you're going to have to do. Yeah, so there are several options that you can do here. Yeah, but for now, let's focus on two-class classification. So let's make an observation. So if in essence, we can write LDA and LRC as classifying X in RP as plus or -1 if we have that plus minus 1 X transpose times some V, some fitted V, is greater than 0. Okay, and this is of course respectively, because we have these two signs here. So respectively, and this is for some V, as I said, some fitted V that it comprises some V naught, then some V hat. Yeah. Okay. So therefore, by having this view, what we have is that we can interpret, the meaning or the impact of a given parameter that is, in this V hat quite easily. Yeah? Or we understand the influence on the classification quite easily. And we can also even understand it in terms of the regressors, just by looking at the changes in them as we change the parameter. And therefore, it's giving us simplicity and interpretability. Now, there is one thing that we're missing here, and it's that we're doing classification, so there is a fair question as to what is the intuition for the underlying classification boundaries, right? I mean, do we have any idea of how they look like just by looking at this? So generally not. And so what we can do is to keep this simplicity, but actually try to explicitly model the classification boundaries so that we get intuition for those as well. Yeah, and this is the idea of the section, basically. Okay, so so what do we do for this? Well, so we keep modeling therefore the regressors. So okay. Okay, so keep modeling these guys as in logistic regression classification, and fit. So rather than by MLE, now fit B, which is just some beta underline differently. How do we do that? Well, we choose this beta, which is again written as this. That's not very clean. Okay, such that this has norm 1, and this is only applying to the second part of the of the previous vector, and such that the following hyperplane. So how do we define this hyperplane? Well, it's a set of R of x's in x, excuse me, in RD. But anyway, I mean, we can, okay, so RP, so this is what we are assuming, such that this equals 0. So that's the definition of a hyperplane. And so what we assume is that this hyperplane has largest margin margin between classes. Okay. So how do we set up this mathematical problem? So since this product here, if you don't remember this, you should remind yourselves that this is the distance between h and x. Okay. What we have is the following. So we can write the beta. We can write the beta as the argmax, beta not in the real numbers, and then beta just that in RP, and again such that it is it has norm 1, and this is subject to yi. This is the observation, the ith observation for the response, times this quantity, which is the product of the 1x times the beta. So this is greater than or equal to capital M, and this is for all, oh dear, what just happened? Okay. And this is for all seems to be a bit temperamental today. iPad. Okay, so for all data points, yeah, we did this. Okay, so it should be clear, right? Because what we said is that this guy is the distance, right? So this is the distance, and so what we want is that, well, when you have, when you're on the label 1, then it's just the whole distance is greater than or equal to capital M, and this distance to some capital H. And then the guys on the other side, we also want their distance, but we multiply it by -1 because the distance is going to be negative if you go underneath the hyperplane. So then we multiply it precisely by the label, and this is the reason why we're choosing the -1 and 1. It's just for convenience. And so what we're saying is that we want this capital M to be, we want to maximize the capital M. Yeah, so this is something I just wrote. I had forgotten it in the statement, and that's of course what we wish to optimize. So we wish to have as large M as possible. I'm not saying margin because it's nearly the margin. So the margin, so 2M. 2M star M star as optimal. M is the margin, okay? Because we have, 1 M for each side. And I'm talking about the margin just simply because that's how I introduced, the potential solution that we're going to be looking at, okay? Now, the problem, of course, is that this is assuming that we can perfectly separate the data, yeah, which is not always the case. So, however, data is not always perfectly separated. Okay, so what do we do? Well, let's introduce some new variables. So xi1, xin, we call these slack variables, okay? So for xi1, xin, slack variables, and then some capital N greater than or equal to 0. We're going to redefine our beta. So let's have the previous one up there. So our beta now is going to be still the argmax of this M over, beta naught being in R, and then beta being in RP, such that its norm is 1. But then now this is subject to, so this is subject to the same as before, but with more conditions, yeah? So we have that the yi times our, and then, okay, let's keep on writing it like this. So beta, so we write this greater or equal to capital M, but remember now that this may be too stringent. So let's now introduce these xi's, okay? And the xi's are gonna have to be greater than or equal to 0. And this, these conditions are for I equal 1 to N. And then the extra condition that we make is that the sum of the xi's is less than or equal to capital N. Okay, so it's all that set of conditions that is subject to the optimization problem. Okay, so let's then sort of see, get a bit of intuition as to what's going on with the slack variables, because these are the new subtlety that we've been introducing. And so we have a few options. So we have the xi is in 0, 1, right? In which case, what we have is that we're allowing xi to be within. Oh, excuse me. So I've forgotten the subscript here. Have you just seen what I changed? So I added subscript here, yeah, of the xi. So that's important, of course, because we're doing this for every data point. And then I feel I forgot it here too. Yes, I just added it here. Yeah, just for clarity, it's here, the xi. Yeah. Okay. Okay. So this means that xi is going to be within distance M, okay, to the decision boundary. So we are allowing it to not be, to not every point be at least capital M distance from the decision boundary, but some of them, those that have these xi's being between 0 and 1, well, they will be just a bit less than capital M. But we could even have this guy being greater than 1, right? So we've said they have to be positive, but it could be them, therefore greater than 1. And in that case, what we get on the right-hand side of the first condition is that the projection is actually negative. Yeah. So what does that mean? Well, it means that the yi times, or let's directly say that the sign of this guy and the sign of this, so these are different. Yeah. What am I saying? Excuse me. So yi is distinct from the sign these, and let me now write the hats, because of course this is, once we've done the optimization problem. And so this means that xi is misclassified. Okay, and that's not really a problem, right? Because in LDA, we already misclassified points, and so do we with in logistic regression classification. If you've I don't know, if you've played around enough with the practical, you'll see that, and we'll see it anyway. Misclassification is not terrible, because at the end of the day, we will not be able to linearly separate things in general. But the good news is that due to this condition, we have at most capital N misclassified points. Okay, and let me just say, okay, no, that I will put in practical. So let's just define then the estimator, the classifier, so definition 14. The support vector machine classifier, or soft support vector machine, is given by SVM X, and this is going to be, therefore, we're looking at two classes, remember, so this is the sign of this. Yeah, so we classify X according to the sign of this. Okay, and of course this guy is as above, and N is greater than 0. Yeah, why am I saying this? Well, if N is equal to 0, then just look at the problems. So if capital N is equal to 0, then we don't have this condition. Then all the xi, well, we do, but all the xi's are 0. And if all the xi's are 0, then we're back to the original optimization problem that I gave. And so this has a name, actually. So if N equals to 0 and the classifier exists, because it may be that it doesn't, right? Because we may not have perfect separation. Then we call this the optimal separating hyperplane. Okay, or hard margin SVM. Okay. Okay, so let's begin just a bit with nonlinear classification. And so the first idea essentially is to try to modify the existing linear classifiers into nonlinear classifiers. Okay, so rather than creating a completely new idea that is, linked to nonlinearities, then let's just try to transform them so that we have a nonlinear transformation. Yeah. Okay. So so this is the kernel, which you may have seen in a different course. So kernel method. Okay. So I guess so just the interpretation here as to what we're going to do is that linear classifiers, as we've seen, are simple and interpretable. But the problem is that in real life, things, even if they're not perfectly separated, but still, they intersect and all of that. The problem is that they still are rarely separated well with linear boundaries. Okay, so they're just simply not complex enough. Now, the key observation here is that if the data is embedded into a higher dimensional space, which could even be infinite dimensional, then it is the case that if you've done it correctly, then generally the classes will be perfectly separated. Of course, finding this, this embedding is exactly solving the classification problem. So it's not simple. It's not necessarily simple, but nonetheless, we can still try to find it, right? And so if we embed then the data points in this high dimensional space, if they're going to be perfectly separated, then we can apply a linear classifier to them, right? Once they have been transformed, right? So that's the key idea of going from linear to nonlinear through the kernel method. Okay, so so maybe what I want to do. Okay, so let me give you the idea then. I don't think we can get around that idea. So we just that I introduced the notation. So for X in calligraphic X, that is now general. So I'm not saying that this is a Euclidean space. We can just take any. So this general, let phi, so X going to phi X, phi 1X, phi 2X, and so on. There's going to be a feature map. Which is this embedding that I was talking about. And, it's called so because it has features phi 1, phi 2, etc., which could be infinite. Yeah. Okay, so now we can apply a linear classification algorithm, linear classifier, to transformed data. This, of course, gives us a nonlinear classifier. Well, it will generally give us a nonlinear classifier in the sample space, so in the original sample space. Okay. And then commonly, what we make as another observation is that commonly, and it is the case for the previous linear classifiers, commonly the linear classifier can be written solely via quantities of the form of a linear product or, here in this new view, what we're going to have is phi x, with the transformed data, and we can call this something, right? We can call this simply k of x and x prime, and this is going to be a kernel, okay? So kernel and the kernel method. So in the kernel method, we're going to view our algorithms as, rather than embedding the data into phis, we can directly introduce a k, so a kernel that is a function of the x and the x prime, and bypass the introduction of this feature map. And so the question that is outstanding now is whether that is equivalent to introducing the feature map. Okay, and this we can answer theoretically, but I don't have time to introduce it now. So I don't have time to introduce it now, so I will do in the next lecture, but I think I'm going to leave it in the theory notes just so that you take a look at it before the practical, so that things make sense. Yeah. Okay, so that's enough for today, and I close the session here, but I do have a few questions. I think, shouldn't the classifier be argmax? I ignore which one of them is the one that
it was for the LRC.
Did I write argmin? Oh, I did. I'm sorry. Yes.
For the LRC, you put argmin.
Yes. Right. Yeah, totally.
Thank you.
Yeah. So let's say argmax here. Yeah. Thank you. Is the half margin capital M above assumed to be non-negative? It is, but I guess, let me just think, because I presume what you're saying is, what about, do you mean?
Well, what I mean is that you said there's the sort of hard margin support vector machine classifier, where if you take the sort of version without the slack parameters, presumably, yeah. So if the classes aren't perfectly separated, there'll be no solution for M being non-negative, but you presumably could still have a solution.
Well, if you have
with some negative M, there's a reverse margin.
Yeah. I mean, I guess you could have that, and then just simply, and just take the margin to be very, very negative then, right? And try to put all of those data points. And then probably the problem with that is that you wouldn't have a uniqueness. So yeah, okay. So then, yeah, I mean, I was silently assuming the capital M is positive, but I guess what you're saying is,
okay,
let's add here the condition of this being greater than or equal to 0, which doesn't matter whether we take it to be equal or not. Yeah, but I mean, we're of course talking about a margin, right? So margin wouldn't make sense to. So I was silently assuming that capital M is positive. Yes. Yeah. Thanks. Any other questions?
I had a question.
Sure.
After the last lecture, there was still some confusion